Hi, welcome to the second session of the oscillation, or you can say about the SHM. In last video, we have discussed about the definition of SHM. Then we have discussed about the equation of SHM. That was a differential equation, and we have solved the equation and got the solution as yt is equals to a sine omega t plus y. Now let's discuss more about this equation. When we ended the last video, we have discussed about the amplitude, phase, and period. Let's discuss more about this amplitude, phase, and period. Amplitude. Amplitude is the distance displacement of body executing the SHM. That is the displacement from the mean position to the equilibrium position, right? So looking into this equation, this is maximum value of sine theta is +1 and minimum value of sine theta is -1. So the maximum amplitude possible here is a and the minimum amplitude possible here is -a, and obviously the equilibrium position is 0. So the amplitude of this equation is a here, that is distance, or you can, sorry, this is displacement of a body executing a system on either side of mean position is called the amplitude. So means any body performing oscillation from the equilibrium to any of the side, we are taking only one side. This is the amplitude. Say this body is performing the SHM here, and say this is minus a side, this is plus a side. So body is moving from this 0. Total displacement is 2a, but if you are asking about the amplitude is from the equilibrium position to the mean position. This position is called the mean, positive mean position, and this is the negative mean position. Second thing is about phase. Phase of an oscillation. Phase is defined by the theta. Theta is equals to omega t plus phi. In the equation yt equal to a sine omega t plus phi. This omega t plus phi is called the phase at any instant, or we can say at t equal to 0, theta will become phi, and this phi is called the phase constant. That is, at t equal to 0 will get the phase constant of the SHM. Positive and a negative direction of motion of SH, simple harmonic oscillation, at any time can be known as phase. At any interval time, it's called the phase. So coming to the next, that is period of an oscillation. Period, for the period, let's say yt equal to a sine omega t plus phi, and displacement at any instant t. Say, now we know the period of sine function is 2 pi, that is omega t plus phi plus 2 pi. We can write this. This is the period of the sine function. Now I can say the sine omega t plus phi plus 2 pi. So I can, let's say the omega be common, taken out as common, become t plus 2 pi by omega naught, right, plus phi. This is some equation like kind of the equation a sine omega t plus phi in this form. So now I can say the time period over here is 2 pi by omega naught. This is their time period. 2 pi omega naught is a period of the oscillation, or you can say it's a time taken to complete the one oscillation. One oscillation, time required to complete one oscillation, right? Now here is omega is what? While driving this equation in the previous video, we come to know that this omega naught was, we assumed that omega naught was k upon m. K was a spring constant, m is the mass of the body attached to the spring system, or of any mass attached to that system. So like we can say t was 2 pi by omega naught, and now we can say this is equal to t pi m upon. Now this time period is, we can see it's dependent on the mass and the spring constant. So we can say if mass is more, if mass is heavier, it means this quantity is more, therefore t would be more, therefore time period is more. If time period is more, it means it requires more time, ज़्यादा टाइम लगेगा उसको ऑसिलेशन करने में. इसका मतलब जो ऑसिलेशन है वो स्लो है. Oscillation is, so we understand that if mass is heavier, we have the slower oscillations, or you can say more time period. And about the spring constant k, and it's dependent on the k also. If we have the hard spring, that means k is more. If k is more in this equation, 2 pi under k by m by k. If k is more, time period is less. T is less, therefore we can say oscillation are small. So for the good kind of oscillation in the spring system, we require less mass and hard spring. About the frequency and angular frequency. Number of oscillations performed performed by oscillator in 1 second is known as frequency. That means एक सेकेंड में जितने भी ऑसिलेशंस होते हैं, number of oscillation happen in 1 second is known as the frequency, and the unit of frequency here is second inverse, right? Or you can say hertz. Hertz was scientist, and in the honor of the scientist, it was the unit of the frequency. And about the angular frequency, there's difference. Angular frequency and frequency. Angular frequency is what? So omega naught is equal to 2 pi f naught. That was frequency above, or you can say 2 pi by t. Or therefore the unit here is radian per second. This is radian per second is the angular frequency. Now let's discuss next about this oscillation about displacement. You know about displacement, and then we'll discuss about the velocity. Then we'll discuss about the acceleration. About this displacement was yt equal to a sine omega t plus phi, and therefore for the velocity we know that this is dy by dt, which is equal to a omega sine omega a omega cos omega naught t plus phi. This is the dy by dt, that is the velocity here, right? Or you can say this velocity be a omega. This is cos omega t plus phi. The cos omega t plus phi is 1 minus sine square omega t plus phi, right? 1 minus sine square omega t plus phi. Now let a transform here. I'm shifting a inside this square root. This becomes omega. Inside this is a square minus a square sine square omega t plus phi. Thus a square sine square omega t plus phi is what? Y square. This is a sine omega t plus phi. This is a square sine square omega t plus phi. Therefore I can say this velocity be omega under root of a square minus y square. This is the velocity, right? Now this is a omega naught under root of a square minus y square. It means this is the positive. It means velocity at any moment. Now this is come with the positive signs. We can say velocity is in the direction of the motion. That means if y is positive along the positive axis, then v is also along the positive. If y is negative, then v is also negative. That means v is positive for y positive, and v is negative for y negative, right? And the important thing over here is this is v omega under e square minus y square. When y is 0, in this equation y is 0. Y is 0 when the position is equilibrium position, right? At the equilibrium position, if y is 0 and the velocity is what? Omega. This is the maximum velocity possible of the oscillation. This is the maximum. So we can say at the equilibrium position we have the maximum velocity of the system, right? If anybody oscillating, its equilibrium position has a maximum velocity. On the other hand, at the end points, y is what? A. That is ends. At ends y is a, then v is 0. That means at the end position, right? At the end position, velocity is v, that is minimum. That means we got the minimum velocity at the end points and maximum velocity at the equilibrium point, and it's positive in the positive y direction and negative in the negative y direction. This was the about the velocity. Now let's talk about the acceleration also here. So if we come to know about the dy by dt was a omega naught sine omega naught t plus phi. This was the dy by dt. Now again differentiate it. If t square by dt square is what? A omega naught square, right? Sorry, here it was cos. Here was cos a naught omega cos. Now the differentiation of cos theta is minus sin theta. This is minus sine omega naught t plus phi. This is minus a naught omega square sine omega t plus phi. So this thing is what? Including this thing is what? This is what? Y. So we can say this is t square by 1 dt square is minus omega naught square y. So this here is the negative sign here. So the negative sign says that in the positive y direction, y is positive, then we have the acceleration is negative, right? And this, when the y is negative, we have the acceleration is positive. Remember this thing, because it's not sometimes not written in the, sometimes it's written not written in the books, so be aware of it. And at y0, y0 means equilibrium position. You know that at equilibrium position there was maximum velocity. Now let's calculate the acceleration here. Y0 means acceleration here is 0. At end point, that is y is equals to a, at end ends b, there was minimum at ends there was maximum there was minimum velocity. Here acceleration here is minus omega naught square, that is maximum acceleration. Here it is the maximum acceleration, right? So at y equal to plus minus a, we have the expression minus plus omega naught square a. Why I'm writing minus plus? Because in the positive direction we have the negative expression, and in the negative direction we have the positive expression. So let's summarize this thing. We have the displacement, we have the velocity, we have acceleration. We have the displacement is calculated y is equals to a sine omega t plus phi, right? And in these terms it was y is equals to omega naught under root of a square minus phi square, and here it was minus omega naught square into a. And about the velocity at equilibrium, that means omega y is 0, and here y is omega naught a, that is maximum, right? Maximum. And acceleration here is was 0, that is, and y is when positive, velocity is positive and acceleration is negative. When y is negative, we have this negative and this is positive, right? And when y is maximum, that is plus a, we have this velocity as 0 and expression is minus omega naught square, that is negative. When y is minus a, we have y is, there is 0 and here is positive acceleration, right? So this is somehow we have summarized the acceleration and velocity in displacement. In next video we understand the system in terms of uniform circular, then we'll discuss about a simple pendulum, and then we'll discuss about damped oscillations. Thank you for now. Have a nice day.